Welcome. Today we're exploring Nemotron 3 Super, NVIDIA's new open, efficient large language model that combines two powerful ideas: mixture of experts and hybrid Mamba attention architecture. The result is a 120 billion parameter model that keeps only 12 billion parameters active at any moment, delivering both strong accuracy and blazing fast inference speed. Why does this matter? Large language models are getting more capable, but deploying them is expensive. Inference is slow, memory is tight, and costs are high. The field needs models that are not just accurate, but fast and memory efficient in real deployments. Nemotron 3 Super targets exactly this gap, achieving accuracy on par with 120 billion parameter rivals while dramatically increasing throughput. The headline result speaks for itself. Nemotron 3 Super achieves comparable accuracy to GPT-OSS 120B and Qwen 3.5-122B across popular benchmarks, while delivering up to 2.2 times higher throughput than GPT-OSS 120B and up to 7.5 times higher throughput than Qwen 3.5-122B. These measurements were taken on B200 GPUs with 8,000 token inputs and 64,000 token outputs. How is this possible? Three architectural innovations work together. First, latent MoE, a novel sparse expert design that improves accuracy per parameter and per compute operation. Second, a hybrid interleaving of Mamba 2 blocks with sparse attention, which slashes memory overhead during generation. Third, multi-token prediction layers that enable native speculative decoding, accelerating inference without a separate draft model. Let's dig into latent MoE. In a standard mixture of experts layer, each token is routed to a small set of expert networks in the full hidden dimension. The bottleneck is memory bandwidth, reading large expert weight matrices, and communication overhead when routing tokens across devices. Latent MoE breaks this bottleneck by projecting tokens into a smaller latent space before routing and expert computation. Here is the latent MoE design. Tokens are projected from the large hidden dimension down to a smaller latent dimension before being routed and processed by experts. This reduces the memory bandwidth cost and all-to-all communication by a factor equal to the ratio of hidden to latent dimension. The savings are reinvested. Both the total number of experts and the top K active experts per token are increased by the same factor, expanding the model's expressive capacity at similar inference cost. The architecture stacks 88 layers following a periodic interleaving pattern. Most layers pair a sparse latent MoE block with a Mamba 2 block, which processes sequences in linear time with a constant size recurrent state, dramatically reducing KV cache memory. A small number of full self-attention layers are inserted as global anchors, preserving long-range information routing across the stack. The model supports context lengths up to 1 million tokens. The third innovation is multi-token prediction. Instead of training the model to predict only the next token, MTP trains it to predict several future tokens simultaneously. This improves representation learning and enables speculative decoding at inference time. The auxiliary prediction heads draft candidate tokens, and the main model verifies them in one forward pass. Nemotron 3 Super uses shared weights across MTP heads, making the drafting head robust to longer autoregressive rollouts. This chart shows the throughput latency trade-off on Blackwell hardware. Each curve corresponds to a different speculative draft depth. As we increase the draft depth from 1 to 3 tokens using MTP, the entire Pareto frontier shifts, delivering more output tokens per second at every latency target. This confirms that MTP's acceptance gains translate directly into better serving efficiency in real deployments. Pre-training ran on 25 trillion tokens in 2 phases. Phase 1 covered 20 trillion tokens, emphasizing broad data diversity. Phase 2 covered 5 trillion tokens focused on high-quality sources. Crucially, the entire model was trained in NVFP4, a 4-bit floating-point format, making this the first large-scale stable pre-training run at this precision level. This required careful treatment of different layer types, with attention and MTP layers kept in higher precision to preserve stability. Post-training followed a 4-stage pipeline. First, supervised fine-tuning on over 7 million samples, including a large proportion of agentic tasks. Then 3 reinforcement learning stages. Multi-environment RL from verifiable rewards across 21 diverse environments, including math, code, safety, and tool use. a dedicated software engineering RL stage using real GitHub issues, and finally, reinforcement learning from human feedback to polish instruction following in safety. The SFT data pipeline puts special emphasis on agentic scenarios. This diagram shows the construction of the agentic command line interface dataset. Starting from a taxonomy of 24 action types, tasks were generated and filtered, then trajectories were distilled from high-performance open-source agents interacting with real CLI environments. The result is training data that teaches multi-step reasoning, long-horizon execution, and autonomous tool use. Looking at the SFT data blend, you can see the breadth of coverage. The blend spans chat, math, code, agentic programming, software engineering, multilingual, and instruction-following data across more than 7 million total samples. Agentic tasks occupy a significantly larger share here than in previous Nemotron models, reflecting the strong focus on autonomous multi-step capabilities. After post-training, the model is quantized for efficient deployment. Post-training quantization produces two checkpoints, an FP8 version for Hopper GPUs and an NVFP4 version for Blackwell GPUs. The NVFP4 checkpoint uses a hybrid recipe, weight scales chosen to minimize quantization error, dynamic activation scaling at runtime, and an auto-quantized search that selectively promotes sensitive layers to higher precision, all while preserving the throughput advantages of 4-bit weights. On benchmarks, Nemotron 3 Super holds its own against much larger or slower models. On AIM 2025, it scores 90.2, competitive with GPT-OS S120B at 92.5. On SUE Bench with open hands, it reaches 60.5%, well above GPT-OS S120B's 41.9. On long context ruler at 1 million tokens, it scores 91.6, while GPT-OS S120B drops to just 22.3. All of this while delivering up to 7.5 times faster throughput. To summarize, Nemotron 3 Super is a 120 billion parameter hybrid Mamba attention mixture of experts model with only 12 billion active parameters per forward pass. 3 innovations: latent MoE for hardware-aware sparse scaling, hybrid Mamba attention for memory-efficient long context generation, and multi-token prediction for native speculative decoding, combined to deliver best-in-class throughput without sacrificing accuracy. The model is fully open-sourced on Hugging Face, including base, post-trained, and quantized checkpoints.